All right, so we stopped here this morning with fairly basic notions, local optima and this construction. That essentially what we mean by local optima is that if you pick a direction inside your feasible set and move a little bit along that direction, you don't improve the cost function, so you actually increase it. And these notions are like really central in building the necessary and sufficient conditions of optimality for local optima. And this is super simple, but it gets very quickly intricate, so that's why I'm preparing that a little bit. First observation, and here we're just talking about an unconstrained minima in some sense. When we compare moving a bit along D on that function to the point itself, you can form a Taylor expansion if your phi is smooth enough, which would look like this. So the first order and second order contribution of moving along D of a tiny bit alpha. And from that you can already derive simply the conditions of optimality if you don't if your D is free in some sense, if you can move in every direction, and that's essentially that the gradient has to be 0 and the second order derivative, the Hessian, has to be positive. That's valid, of course, only if you can pick any D you want, right? So if I can select any D I want in my space of decision variable, then I need these things to hold, like the gradient 0 and this is positive definite. So that this will always be positive for alpha small enough. But that's only if D is completely free. Once we are on some constraints, then these things will be different. Does it make sense? Yeah. Okay, and that's, of course, the conditions of optimality for a non-constrained problem. So you see that in high school already, I guess. So the first order condition, the gradient of the function is 0. That's simple. And the second order sufficient conditions, we often call them SOSC. You see that popping up in the literature quite often because they are quite crucial in NLPs and when we treat them. We'll discuss that later. So if you have that the gradient is 0 and the Hessian is strictly positive definite, then you have a so-called strict local optimum, which is essentially saying that the point here is really lower than its neighborhood, so the function is curved up if you want, and you would have a strict local maxima if you have the opposite. So essentially if you have this situation here, you could have something in between, so maybe that you don't have a strict inequality. And that could happen, for example, if again you have a function that looks like this. So you're essentially flat here, in which case you would not want to talk about this strict local minimum or maximum if it's the other way around. It happens especially in higher dimensions where you may have curvature in some directions and you may have some flat direction somewhere else. So you have a direction in your decision variables that does not impact on the cost locally. And then you have a situation where you have some 0 eigenvalues. So in principle, locally, you could move along that direction and not increase the cost. And just again, to insist a tiny bit on that, so the gradient being 0 means that there is no D such that you can move down that gradient, right? If the gradient is non-zero, and D is free, you could move along that direction and go down with a cost function. You would have a D that decreases the cost. And since this guy, if this guy is positive definite, then there's no D that would make this quadratic form negative, or put differently, any D you can pick will make this thing positive. So to first and second order, you essentially only can go up with your cost function when you move. Is that clear? Yeah. So essentially that's this philosophy. So if you have a local optimum, that means no direction can improve the cost locally. You cannot move somewhere to improve that. Okay, let's talk a bit about regularity and describing feasible direction, because what's going to happen next is essentially once you introduce constraints in the problem, this D that you want to try to follow to see if there is some direction where you can improve your cost function, like reduce it, will be somehow restrained by the constraints. You cannot move into forbidden directions that are not allowed by the constraints. And it turns out that there is quite a few nasty things that can happen behind this, and that is at the core of most of what goes wrong in solving optimization problems in practice. It has to do with regularity. So I want to discuss that a little bit. I'm just curious, do you know about these regularity questions behind the Kkt conditions? It's actually going into unknown territory, or yeah, okay. Okay, let's go there then. It's gonna be interesting. So essentially what happens once you have constraints is that this D that we need to check to see if there are directions improving the cost will be blocked in some sense by the constraints. I mean, I made this sketch this morning, which is probably quite obvious. So if, for example, you restrict your, let's say, W to be positive, then the D we're talking about is only moving in that direction, right? It's kind of obvious. Becomes quickly more complex with a number of constraints and different things, but that's really the idea here. So we'll still focus on this. No admissible direction can improve the cost locally, but we need to discuss what admissible directions mean. So here's my picture. In that context, if that's through your cost function, the free minimum is down here, but you have this constraint W larger than or less than 0 actually, and the admissible direction is only like away from the constraint if you want. I can push that in higher dimensions. Here is, for example, a cost that has its minimum there, and then I say introduce this affine equality constraint here, so the point has to be on this red line, and the solution will be here, and essentially what's happening there is fairly obvious. So the D along which you can move is along that line, obviously, right? And what this condition is saying is that essentially if you try to wiggle this point in these directions, you cannot improve the cost. So I guess visually it's fairly clear. Yeah, makes sense? Yeah, okay. So that's kind of obvious, but it quickly becomes more complicated. So let's try to put a few things. So we discussed the feasible set. So essentially the set of points that satisfy the constraints. I'm talking about equality constraints here. We'll start there because it's a bit easier than inequality constraints. Yeah, let's talk about that. So this notion of regularity, and let's define it first. I will call a point regular if the essentially you can read this as a gradient or Jacobian. Essentially, when you take the derivative of your constraint function with respect to the variables, this thing is full column rank, i.e. Maybe I can specify a tiny bit what that means. So by this thing here, I really mean the gradient of the first constraint, second constraint, and so on, right? Each of this is a vector. And what I'm saying with full column rank is that I don't want that these vectors become linearly dependent, right? It's all good for everyone, right? Yeah. And here is an example, just to prime you a little bit on the fact that things are not obvious and simple. So here is an example of a feasible set that would be regular everywhere. So what did I do? I wrote down two constraint functions, G1, G2. G2 is actually a simple plane, it's linear, fine. And G1 is something cubic. But just please note that both functions are completely smooth and very simple. So that's the G1 and G2. And if I talk about the feasible set, now both, like the set of points that satisfy both constraints, there will be this intersection here. I repeat it here. So it's a nice smooth curve, right? So that looks good. If I build this Jacobian of the constraints, I find this this matrix here, and I'm gonna check in this case the dependency between these two vectors, right? And turns out that on this specific set, I don't have any problem. You don't have any points on this specific curve such that these two vectors will become dependent. You can verify that. Now you would need W1 to be 0 to make a dependency here, and then the W2 would be non-zero, so it just doesn't happen. So all points in S would be regular, so would have this property. But now let's make a very small change. I'm just moving the plane downward a bit. So I still have two nice and smooth constraint functions, and they look good. But now what happens is that the intersection of these two constraints actually looks like this. And so you've generated a very nasty, like kind of pointy, non-smooth curve by intersecting these two things. And that's actually, that's going to be an irregular point. So essentially, this regularity condition is kind of about is the manifold or the set of points you are building by intersecting your constraints, will that thing will be let's say nice and smooth. At this point, actually, you have you have 0, 0. So W1, W2 are 0. So you have basically 0, 0, minus 1, 0, 0, 1. So this Jacobian is rank deficient, and you end up with a point like this where you have like very nasty object to deal with. Okay with that? Yeah. And that's a big red flag, I would say, because you would not guess a priori that mixing these two constraints would be creating problems, right? You really have to go into checking this Jacobian to see that something is happening there. Okay, now how do we describe these feasible directions, these Ds along which I can move? It's called a tangent cone, and it has a very nasty definition, actually. This thing here. Can try to unpack it a little bit, what it means really. It's one of this little game where you try to create a series of points with some properties, and where these points are converging will be your construction. So I'll just do it for this regular point first. So that was when the plane was a bit higher and creating a nice manifold here. So what do we mean by building that? Well, first, I will pretend that the outcome of this construction would be this line here, which is basically at this point, which is basically the tangent, the curve at this point. And what is happening in the construction is essentially, here is an example of a sequence of Wk in S tending to W with associated alpha k, such that this holds. And so you pick a point here on the Wk, you build this like segment here. That's your alpha k, Wk minus W. And you want that this thing, as you progress Wk, will essentially tend to this D. And what's going to happen is as you move Wk closer to the red dots, you pick new alphas, and slowly you essentially tend to this point here. And so what's happening here essentially is that your tangent cone is basically the classic tangent to this curve here. So essentially, I could, in this case here, build this weird set by really taking the tangent of my curve at this point. However, if we do the same construction, well, maybe state that. So this point is regular. We've checked that before. And essentially what happens is if the point is regular, this strange set that is a little bit nasty to build, I mean, you need to work on a series of points and verify convergence conditions. Doing this is the same as essentially evaluating the set of directions that are orthogonal to the Jacobian of the constraints, right? The way you would normally build the tangent to some object like this, right? Just check the directions that are orthogonal to the gradients of both constraints. If we do the same construction on the irregular points, here is what happens. I just look at the situation from above. The D that you build from that object, that's the genuine tangent code is actually this thing here. And it's actually correct. What happens at this point down here is that the two sides are like collapsing into like vertical lines. And indeed, very locally, you should look at this thing here, this curve, as pointing upward. Of course, if you try to take the null space of this thing at this point, it will give you something a bit strange. So in that context, if you try to build the tangent cone, again, as you'd have the WK that tends to the point where we are checking this tangent cone, and you adjust the alphas accordingly, and you would get that, right? So this red D is a valid tangent cone because you can make that construction for that D. And so indeed you get this line up here. So the tangent cone at that point, it's irregular. It's essentially this direction alone. So in 3D it's 0, y 0. But if you try to evaluate the null space of that Jacobian at this point, then you can actually also play with the x, because this matrix at this point would be 0, 0, minus 1, 0, 0, 1. So these two coordinates are free essentially. Which means that the tangent cone, the set of feasible directions D, that's this thing up here. But this guy would let you actually move in all directions. And that's wrong. It's not permissible to, for example, move over there. Does it make sense? So what we're after here is essentially to check the optimality of a point when we have constraints. We would have to build all these directions D where we can move. Our problem is that this is very hard to work with. We don't like that. So we want to replace it by something simpler. For example, working with the null space of a Jacobian. That's easy to work with. And the bottom line is that we can replace this complex stuff by that simple stuff if the point is regular, right? Then you can work with this constraint gradient. And that's the example where things don't work properly. Does it make sense? So when you build the Kkt conditions, we'll get there, but essentially that's one of the things you're doing. You're pretending that the tangent cone is given by the null space of your Jacobian of the constraints, and that's true only if you have a regular point. Okay? Okay, so let's have a look at how we get to the Kkt conditions. And I'm trying to illustrate these things in this kind of picture. So it's a bit barbarian, but it should be okay to understand that. So what do we have here? I'll pretend that this is my feasible set S. So essentially, I'm imposing some constraint on my point, and this things here would be the level curves of my cost function. So my minimum could be somewhere down here possibly. And that will be the optimum of my problem, my W star. What happens at this point is essentially this. So I have the gradient of the cost pulling there, and if I take, so no, sorry, that's the gradient of my costs, and I want to move down there, and that's the gradient of my constraint at this point here. What we are essentially having here, so that's the tangent cone. My point is regular here, it looks that way at least. So I basically work with a classic tangent. Yeah, and so my conditions of optimality in this context is actually saying, from that point, if I wanted to decrease the cost, I would have to move in a direction that is opposed to the gradient of the cost, so I have to move down there. But the only directions I'm allowed to move in are in the tangent cone, and that's orthogonal to my gradient of the cost, right? So I can only move along this pink line, but I would like to move along this in order to decrease my cost. So you can see conditions of optimality in this geometric sense. And another way of restating this condition, so there is nowhere to go to improve the cost from W star, is essentially by saying there is no direction D, such that I move downward the slope of the cost function, so I move along the opposite of the gradient, and such that at the same time I move in the tangent cone of the constraint. So I move orthogonal to the gradient. That's your gradient tangent cone. And the fact that you can replace moving in a tangent cone by this condition is because the point is regular. Otherwise, you could not do that. Okay with this? Yeah. Now, actually, so the transition from that condition to the Kkt conditions in the equality constraint case is based on the forecast lemma. It's not completely obvious. If you're trying to prove that into thin air, it would probably not be so easy, but here is the statement. And that's actually a little bit important to understand the logic behind the Kkt conditions. So I'll repeat that a few times because they are not straightforward. So what they are saying is that essentially if a point W is a local optima of the problem, right? And W is regular, so you have this condition on the Jacobian constraints, then there is a vector lambda, such that you satisfy the Kkt conditions. So these are the Kkt conditions in the purely equality constraint case. So what do we have in here? Essentially, we are simply saying that, well, first, obviously, the equality constraints have to be satisfied, and a bit less obviously, but it's not completely difficult to understand. Think of the scalar case here, or actually we have two dimensions. Essentially, we're saying that I need to be able to sort of align my gradient of the cost and gradient of the constraints on a single line. So here I have a single constraint. The lambda would be a scalar. And what I'm saying is that if I multiply my gradient of g by the correct lambda, I will be able to cancel out my gradient of the cost. If this gradient was, for example, like this, let's say like this, there would be no lambda such that I can cancel out the gradient of my constraint and the gradient of my cost, right? So essentially, it's kind of saying that somehow my gradient of the cost can be aligned with the gradient of my constraints. In higher dimensions, it's a bit harder to see. Yeah, so these are the Kkt conditions for the equality constraint case. And just once more, so nowhere it is said that if you get the Kkt points it's a local optimal. There's nothing saying that. And it's not said that if you have a local optima, it has to satisfy the Kkt condition. It's more complex than this. So it's only a point that is local optimum and regular that has or is a Kkt point or satisfies these conditions for some lambda. You could have optima that don't satisfy this because they are not regular, for example. You could have solutions to these equations that are not optimum and that are not regular, right? So you need to understand a bit this logic in order to get there. The bottom line is that if a solver finds a solution to the Kkt conditions, it does not necessarily mean that it's an optimum. Do you get that a little bit, this picture? Yeah. We can play a bit in the exercises with this. Okay, just a few comments. That's a system of n plus m equations in n plus m variables. So by n, I mean the dimension of w, and by m, the dimension of lambda. So it's a square system, right? You could solve it for w and lambda if everything is well posed. The lambdas, we call them the Lagrangian multipliers. There's one of them for each constraint. So if you have 1,000 constraints, you have 1,000 multipliers. This first condition is essentially aligning the gradients, is most often written in this form, with L is the Lagrange function, which essentially is simply the cost plus a scalar product between your multipliers and the G, right? Probably have seen this object before. Essentially the gradient of this thing is 0. If you didn't have constraints, this would disappear, and this would boil down again to saying that the gradient of the cost should be 0 for having an optimum, right? Yeah, and we typically talk about dual feasibility for satisfying this condition, which is just saying that the Lagrange function is stationary. Okay with that? Yeah. Okay, so now we can shift gear and move to inequality constraints, and that's most often when you do optimization, that's when you introduce inequality constraints that things become funny and sometimes nasty. So I'll forget the equality constraints for a bit and just talk about inequality ones. So then the feasible sets, this S is now the set of points for which h of w is negative, and let's imagine that it would be that thing here, right? This portion, so really inside these things. So now my set of feasible directions, there will be the d's such that for some small displacement, your w plus alpha d is also in the feasible set. For some alpha small enough, you can read it that way. So, or for all alpha small enough, so between 0 and some small enough epsilon. So essentially, it's the set of directions in which you can move and stay inside the feasible domain. So it basically builds a cone that would be, if everything is nice, essentially tangent to your constraints at that point. So now you want to describe this feasible directions D by essentially using the same kind of argument as before, essentially saying I'll describe my D's as those for which this Jacobian of the constraints times this D are less than 0, right? One thing to be careful about when playing with inequality constraints is that you always need to distinguish between whether your constraint is active or not. Stupid example, if I was evaluating the same questions here, for example, at this point, then at this point I would actually be free to move anywhere, right? I have a neighborhood where I can move. So in that sense, locally, I could disregard these inequality constraints, right? So when we build these feasible directions, we really talk only about locally about those related to active constraints. So if I was here, I would disregard that constraint and only work on locally around here. So when I write nabla HA transpose, I will be really the Jacobian of my H only on those constraints that are active. Right? You good? Yeah. So yeah, if the active set is empty, I'm talking about an empty matrix here, and you could read that as basically a condition that is always satisfied, which would give me then a complete neighborhood around my points inside the feasible domain. Okay, now this concept of regularity for inequality constraints, that's the same as for equality constraints. A point is said to be regular when you have inequality constraints if the gradients of all the active constraints, right, is all these gradients are linearly independent. So it's essentially the same story as before, but we only care about those constraints that are active. Those are not active, we could disregard them. Actually, it's quite important because you may have quite wrong impressions. When a simple example is if your constraints would be, for example, something like this. These are essentially simply two lines if you want. It's in 1D, but essentially if you evaluate the gradient of that or the Jacobian, you would see that in some sense they are linearly dependent, but only one at a time would be active. So for example, simple bounds on variables, they are always linearly dependent, but there's only one of them active at once, so you don't have problems here. So if you assemble the gradient of all the active constraints, you get a set of vectors. They have to be linearly independent. Then you have a regular point. When you respect these conditions, there is a code name for that. It's called Linear Independence Constraint Qualification, LICQ. You'd also see that very often in papers. LICQ and SOSC, they often come together. Yeah, and that's actually a very good, useful remark. For most of these questions around local conditions and questions in NLPs, when you analyze what happens at one point, you can pretty much treat inactive inequality constraints as if they don't exist at all, and the active ones as if they were equality constraints. Kind of make this, it has this effect if you want. And so if you want to talk, for example, about regularity on a problem that has both inequality and equality constraints, you would want to assemble all the gradients of the equality constraints and all the gradients of the active inequality constraints that are behaving like equality constraints, and check the independence of all these vectors together, right? So if you have the gradient of an active inequality constraint and of an equality constraint that is that are dependent, you have a problem. See if I can sketch something maybe. You can imagine something like this, for example. That's an equality constraint, so I have to be on that line. And that's an inequality constraint, I have to be on that side of this curve. And if you imagine that this h comes like tangentially to that line at this point, so this point is feasible, but at this point, these two things are tangent to each other. So they also have the same, or their gradient is in the same direction. So maybe that's going to be nabla G, and maybe that will be nabla H. And they are not linearly independent, right? So here you have a problem at this point with these two constraints. Okay. Does it make sense, this, or? Yeah. For example, just to complete the picture, if my H was up here, this point would be fine because H is not active at this point. I don't need to check the dependency of the gradient of G with that constraint. Okay. Okay, LICQ is the most often used. It's called a constraint qualification. You have I'll give you a list later in the slides of the different things. That's the most commonly used because it's the most simple to work with. It's just about checking the independence of some vectors. And if you satisfy this kind of condition, then you would most solvers would be happy with that. Maybe I should say something about the logic here. So if you satisfy this condition, so this independence, LICQ, then the point is regular. But you can have regular points without satisfying this, by satisfying more involved constraint qualifications. Okay? Yeah. Okay, so we can build something geometric again on the inequality constraint. So it's the same picture as before. There's also a cost function. You want to go down here. The gradient here should be more like this, but okay. And you have your inequality constraints that force you to stay on that side. So the optimal point would be down here. And so essentially what we are saying, all the geometric conditions, is that there should be no intersection between the directions in which I can move and the directions in which I could improve my cost function. Right? If that set was intersecting that one, I would find directions where I can move in order to improve my cost function. And from an algebraic point of view, we have again a fairly simple statement. So we don't want that there is any direction D along which we could move and decrease the costs, because it will basically go down the slope of the cost function, and at the same time move into directions that are acceptable for the active constraints. And this is a valid way of qualifying the optimum only if the point is regular. So you need to be allowed to use this thing as a way of describing the admissible directions. Okay, so now we can summarize the Kkt conditions for a generic NLP. And so we call a Kkt point this triplet. So you need your W's, we call them primal variables typically. The lambdas, that's what we have seen before. And now we need an extra multiplier for the inequality constraints, the mu. We have the same thing as before. So the gradient of the Lagrange function with respect to the primal variable should be 0. And now these mu's, they are signed. So they need to have a specific sign. Here greater than 0. You need the so-called primal feasibility, so that's essentially that the constraints are satisfied. It's kind of obvious. And when we have inequality constraints, we have this third condition that I'm not sure everyone understands very well. It's called complementary slackness. Essentially saying that these byproducts mu I h I, so for each pair of multiplier and constraint, should be 0. Which is another way of saying that if mu is non-zero, then h has to be 0. If h is non-zero, mu should be 0, right? So It's more like almost a logic condition than an algebraic one. And that's essentially an algebraic transcription of this geometric condition. So all this reasoning about directions along which we are allowed to move and improving the cost, you can translate them into these Kkt conditions. So what I said before applies also in the inequality constraint case. And so these are the first order necessary condition of optimality. So if a point is a local optimum and regular, then there is a vector lambda and mu such that this triplet is a Kkt point. So you can find a lambda and mu, and they are unique such that you satisfy these algebraic conditions here. Now I can mention, I said there is something in between active and inactive constraints, and here is the trick. So we saw that. So an inactive constraint is when h is less than 0, so it's not meeting the bound. An active constraint is when h is at 0, so it's essentially on the constraint. But there is something in between that has to do with the multipliers. So an inactive constraint, remember, you have the complementary slackness conditions saying essentially mu and h cannot be non-zero at the same time. You can have h negative, mu 0, that's inactive. Mu positive, h 0, that's active. So both satisfy this. But of course you have a third case where it's mu and h are 0 at the same time. That could be also satisfying this. When you get that, we are talking about weakly active constraints. Do you ever have this kind of situation? Encountered that before? No. They actually play a very important role in many, I would say, byproducts of solving NLPs and Kkt conditions. So we'll see it popping up again. And I'll tell you in a bit what an intuition of what these things mean. Okay, just one more time, the importance of regularity on a simple example. Yeah. So let's consider this problem. So I have 2 dimensions, W1, W2, and my cost wants W1 to be as large as possible. So I would like to move as far to the right as I can. But I'm constrained by these 2 things. One is W2 is positive, so I can only be up here. And this one is this strange constraint like this that becomes tangent here. So actually, it's kind of a problem that is related to this. So visually, we can easily see that the solution should be here. It's actually going as far as possible in that kind of corner in order to minimize the cost. So that's the solution. Should have no problem with that. However, if you run the math on this problem, essentially you just build a Lagrange function and its gradient. So the gradient of the cost is going there, -1, 0. Gradient of that function at this specific point here, at the solution, 0, 1. And the gradient of the second constraint, also at this point here, 0, -1. So when you assemble the Lagrange function, or the gradient of the Lagrange function, well, we have this one here, that could be 0 if the multipliers are in the right shape. But I have -1 here, that will never go away, right? So at this point, the Lagrange function is not stationary. So what's happening here? So the 2 constraints, the 2 inequality constraints are active at this point, right? I'm touching both. And when I evaluate the gradients, they are linearly dependent, right? 0, -1, 0, 1. So this point, again, even though it looks fine, I mean, visually we see that it should be the optimum of that problem. At this specific point, I fail LICQ. I don't have a regular point. And even though it is an optimum for the problem, it does not have a Kkt point. Yeah, it's not a Kkt point, or I cannot build multipliers to get a Kkt point, right? So these two gradients are aligned, and I have a problem here with the Kkt conditions. So if you think again about the logic in the first order condition, first order necessary condition for optimality, it's if W star is an optimum, as satisfied here, and is regular, then you can build a Kkt point with that solution. Here I fail regularity, I don't get a Kkt point, right? If you throw that into a solver, it will crash in your face. That's not going to be solved. So it's not just like nice theories. These questions are important. And I can make a bit of a spoiler here. If you were try to imagine this problem as an actual mechanical construction, for example, like say you have a slope going to the right, and you have some borders here that force your point to stay in that yellow area, right? And so the point would slide down and come down here, right? I don't know if you feel mechanically what would happen. The point here would basically kind of try to move down into this wedge, and the wedge will kind of crack because these two things maintaining the point here will have kind of infinite forces, right? Do you manage to see that a little bit? Yeah. It's like if you have a wedge in a piece of wood and you insert an axe, it will easily crack because the constraint that keep the point in place, they are actually pushing against each other, not up. And we'll see that you can completely view this problem in that sense. Yeah, that's where I'm going. Because all this stuff is nice and everything, but it's not very helpful in practice. In practice, you want some simple intuitions on what is going on here, and that's really helpful in my opinion. So let's try that. And let me focus on inequality constraints. That's the main difficulty, I would say, in the Kkt conditions. And you can picture this situation. So that's my cost. Two variables, the minimum is here. It's quadratic here, actually. It's fairly simple. But I will put some inequality constraint that forces my solution to be above this thing here. So this is forbidden. Solution would be somewhere here, actually, if you solve the problem. And just, it's a bit naive, but think about this as you have a valley here, and you have a fence. And you just drop a ball, it's going to roll and hit the fence and find the lowest point on the fence, right? Simple picture. And then you can think in terms of forces, really. You have a force on this thing that pulls it down the slope, right? It's given by minus the gradient of the cost function, all right? And then you have a force from the fence that will balance exactly that force here. If it was not balancing the force, the mass would move, right? And that force can only be orthogonal to the fence. So it has to be in the direction of the gradient of this function. And the mu is scaling the force such that it balances exactly gravity, right? So you can read this mu as some kind of adjustment of the force such that essentially the fence is pushing back just enough so that the mass does not move. If these things were not properly aligned, then you would have a resultant of these forces and the ball will keep moving, right? So that explains the stationarity of the Lagrange function. Essentially, this nabla L0 is essentially meaning that the forces on the mass are balanced. Yeah, that also explains why you have a sign on the mu. Essentially, the sign on the mu is saying that the fence can only push back. It cannot pull the ball. So if you were to shift the slope the other way around, the fence would not block the ball. It would let it go, right? So the mu positive means the fence can only push back. If you think about the lambdas on equality constraints, they don't have a sign, because equality constraints, they can restrain the mass in every direction, right? They can push or pull. That's why the lambdas are not signed. So if I animate my problem a little bit, I will move the fence, and you can actually really see these forces disappearing. I have less and less gravity, and the fence pushes less and less back. So once you reach this point, the ball is still touching the fence, but it's at the optimum already. So the fence does not need to push back anymore, right? So you get a situation where h is 0, and mu, the force of the fence, is also 0, right? So now you understand the concept of weak Diaclive constraint. That's how I define them. Essentially, the solution is touching the constraint, but the constraint does not need to push back the solution. It's already happy where it is, right? And once you become inactive with the constraints, the ball does not touch the fence anymore, and the fence does not need to push back, right? So mu is 0. And you can also explain this complementary slackness condition in that context. This is simply saying the fence will not push back unless the ball touches the fence, right? It's a logic condition. If h is non-zero, that means the ball is not touching the fence, then mu, the force, should be 0, right? And if h is 0, the ball is touching the fence, then mu can be non-zero. It can push back with the right sign, okay? So I don't know, but for me, I think found it very useful to have these simple ideas in my mind. Yeah, can go back to this question now again. I primed you on this. So what if you fail the elastic conditions? That's the same story here. So you have two fences here, right? And the slope on your ball is pushing down there. And you can really imagine if you try to put two fences and to block a ball, and the fences are really like this, the ball will put infinite forces on these fences, right? And they will open them. And you can have this interpretation here. So the gradients of the h, they are actually aligned and orthogonal to the slope. So essentially, these things, they are supposed to be used to create forces to block the ball from going further. But the ball has a force pushing it down there, and you can only exert forces in that direction from the fence. So what would happen is, I mean, mathematically, you would need infinite mu's in order to somehow balance this force. Roughly speaking, you could think that way. So infinite forces, that's why it's cracking if you want. And you cannot do that. So the Kkt conditions are refusing these points because it's saying, essentially, I have no way of balancing your forces at this point. Okay? Okay. What time is it? 5:10. We can get started with this. Okay, so I just wanted to look briefly at the Kkt conditions for some typical problems. So like, for example, LPs. Because all these notions, you can also apply them on most simple problems. The Kkt conditions for SDPs, they look different. But otherwise, it's pretty much it. So if you write these Kkt conditions for your LP, so that's your Lagrange function, so cost, equality constraints, and inequality constraints. and your Kkt conditions essentially read as linear algebraic equations with that one. You have here the complementary slackness conditions. They are not linear actually, because you have mu and w, and then you have some inequalities. If you knew which active set you have, so if you knew a priori what constraints are active, then you could boil down or rewrite your conditions in this form. So the mu's associated to inactive constraints would be 0, and only those corresponding to active constraints are non-zero. So this product here, you could rewrite it that way. This inequality here would be a simple equality constraint on the active constraints. The mu a's for active constraints are non-zero, and the a bar, that will be the inactive constraints, that will be negative and 0. And you could collect this in a matrix form, which turns out to be symmetric here. And you have these extra conditions on the mu a's for the active constraints and the constraints for the inactive ones. And if you discuss about active set-based solvers, they essentially use these kind of strategies to find the solution. They would try to guess the active set, solve this, and then check these conditions and adjust the active set accordingly. Okay with that? Yeah. For a QP, it's a bit the same story. So you just have an extra term here in the quadratic that comes here in the Lagrange function, comes here in the Kkt conditions. And same story, you can split the conditions between active and inactive constraints. They will become, they will impact the conditions in two different ways. You essentially get the exact same thing with the addition of an h here on this block. And same story as before. QP solvers, like for example QP Oasis, it's an active set solver. It's really doing that. So guess the active set, you form this system, solve it, find w lambda mu a, and then check if it's compatible with these guys. If it's not, you change some active constraints in a smart way, and then and you repeat. Okay with that? Okay, maybe one last slide. That's an observation that is used in a number of contexts, which can be useful or not. It's kind of interesting that if you try to understand what a Kkt point is with respect to the Lagrange function, so this L we have built, it turns out to be the saddle point. It's a minimum along the primal variables and a maximum along the dual ones. So I make here an example, so a simple one variable w, one half w square, quadratic cost, one equality constraint, and I chart here the Lagrange function. So that's L of w lambda in this case, the w's and the lambdas, and the solution of the problem is here. And yeah, if you understand the level curves, you would see that it's a saddle point. Yeah, so if you build the Lagrange function, gradient is 0, so w equals minus lambda. So you have this 1 minus 1 point. And that's used in some contexts. So if you build your NLP and the Lagrange function, you can define the so-called dual function. I don't know if people have worked with that here. Yeah, a bit. Defined by the dual function, essentially the infimum of the Lagrange function over the primal variables as a function of lambda. So it's kind of saying, let's say I know my lambdas and I will minimize my Lagrange function over w. It's kind of saying, okay, maybe the lambdas are here, and then I minimize the W for that specific lambda. What happens is that this dual function is an underestimator of the optimal cost. So the value that is minimum for this problem will always be larger than this d of lambda. And that's used in many contexts. At the solution, that's locally. This bound is met for convex problems. For non-convex, it's often not. But at the local solution, you have this effect that if you move to the solution, this saddle point, by essentially maximizing d over lambda, because it's kind of a maximum over the dual variables, then it's meeting the solution. So that's used in a number of contexts. I guess I will stop here. Tomorrow we will discuss about second order sufficient conditions. Have also a lot of quite interesting things happening there.